So today we discuss Lagrange interpolating polynomials. Joseph Louis Lagrange, an Italian-French mathematician, has published interpolating polynomial of lowest degree in 1795. However, the method was first discovered in 1779 by Edward Waring, a British mathematician. So the first time lowest degree polynomial has been introduced by Joseph Louis Lagrange. So he was an Italian-French mathematician, but the method was first discovered by Edward Waring. So he was a British mathematician. For a given set of points xi, yi, with no two xi values are equal, it means there should not be two equal points in the domain, or you can say that for different points in the domain, the Lagrange polynomial is the polynomial of lowest degree that assumes at each value xi the corresponding value yi. It means this polynomial can act as a 1-1 correspondence or injective functions. The Lagrange interpolating polynomial is simply a reformulation of the Newton polynomial that avoids the computation of divided differences. So what's the difference between Newton's polynomial and the Lagrange polynomial is that Lagrange polynomial don't use these divided differences while Newton polynomial use divided differences. So to compute the divided differences is an extra work. So to save from this extra work, you can use Lagrange interpolating polynomial. So what is the linear Lagrange interpolating polynomial? The linear Lagrange interpolating polynomial through 2 points x0, y0 and x1, y1 can be written as p of x is equal to L0 of x f of x0 plus L1 of x f of x1. So where these Lagrange coefficients can be written as the first Lagrange coefficients is given by L0 of x is equal to x minus x1 over x0 minus x1. And the second Lagrange coefficients can be written as L1 of x is equal to x minus x0 over x1 minus x0. So Lagrange interpolating polynomial, so given in 5.2, can be written in the form of coefficients as p of x is equal to x minus x1 over x0 minus x1 into f of x0 plus x minus x0 over x1 minus x0 into f of x1. So this polynomial is the Lagrange linear interpolating polynomial because here the function this variables involved has the degree 1, and also this is the polynomial of lowest degree, which is the degree 1. So that's why we can call it linear interpolating polynomial. To verify that this polynomial is a unique polynomial, so we can proceed as follows. For the uniqueness, p of x0, so x0 and x1 are two different points in the domain. So we actually have to verify that for two different points in the domain, whether we have a two different points in the range or not. So if we have for two different points in the domain, two different points in the range, then we can say that this polynomial is a unique polynomial because this function is an injective function. So x0 minus x1 over x0 minus x1 f of x0 plus x0 minus x0 over x1 minus x0. So here is, okay, f of x1 is equal to, so this x0 minus x0 will be vanished. So we will have this term x0 minus x1 over x0 minus x1. So this can be divided and we will have this 1 instead of this coefficients. Polynomial. So this is the actually the unique polynomial. Why? Because p of x naught for p of x naught. So we have this y1 y naught or f of x naught, because this x naught minus x naught will be vanished. And similarly, if we this replace x with x naught x1, so x1 minus x1 will be vanished, and we will have this f of x1 is equal to y1. So now, so p of x naught we have for p of x naught is equal to y naught, and for p of x1 we have y1. Therefore, polynomial is unique and of degree at most 1, passes through 2 points x naught y naught, x1 y1. If we denote Lagrange coefficient L naught of x and L1 of x as L10 of x is equal to x minus x1 over x naught minus x1, and L11 of x is equal to x minus x naught over x1 minus x naught, then polynomial can be written as P1 of x is equal to summation k equal to 0 to 1 f of xk into L1k of x. So there are three ways to write this Lagrange interpolating polynomial of degree first, or the lowest degree polynomial. So the one way is p of x is equal to L naught of x into f of x naught plus L1 of x f of x 1. And the second way is that 5.3, we can just put this coefficients x minus x1 over x naught minus x1 f of x naught plus x minus x naught over x1 minus x naught into f of x naught. And the third way is that we can write in the form of summation. So p1 of x is equal to summation k equal to 0 to 1 f of xk L1k of x. Now we can generalize this polynomial to the nth Lagrange interpolating polynomial. So what is the nth Lagrange interpolating polynomial? If for x naught, x1, so on xn, so these are n points from the domain. So n plus 1 distinct numbers because we have started from x naught. And f is a function whose values are given at these numbers. Then a unique polynomial p of x of degree at most n exists with f of xk is equal to p of xk for each k is equal to 0, 1, 2, so on n, which can be written as Pn of x is equal to f of x naught ln of 0 x plus so on plus f of xn ln n of x is equal to summation k equal to 0 to n f of xk ln k of x. So if you just make a comparison of this summation and this summation, so what is the difference? So difference is of only n, because here is L1 of k and here is Ln of k, and here is f of xk is the same in both formats. So f of xk, here is also f of xk, and here is only one coefficient L1 of x. So if we start from 0, we will have two Lagrange coefficients. And if we start from 0 to n, we will have n plus 1 coefficients, n plus 1 Lagrange coefficients, because the first coefficient will be started from 0. Okay, and here, if first coefficient is started from 0, we will have two Lagrange coefficients, 0 and 1. And here, 0 to n, it means n plus 1. And just if we replace this 1 with n, we will have this nth degree Lagrange interpolating polynomial, where for each k equal to 0 to 1 to n. So now we can generalize this coefficients, you see. L1 0 of x minus x1 over x naught minus x1, or you can say that we can generalize these coefficients L naught of x minus x1, x naught minus x1 up to nth order. So how we can generalize? So if we have ln of k of x, we will have this x minus x naught, x minus x1, x minus k minus 1, x minus k plus 1. So just note that we will not have xk as a numerator. So in the numerator, we have no terms of xk. So we have to skip the term xk. You just observe here x minus xk plus 1. So next term should be x minus xk, but we have to skip this term, okay, because it uses here. So that is why x minus xk plus 1. And similarly, in the denominator, just observe the terms. So it's the same terms in the numerator, but just x is replaced with xk. So just observe the first factor is x minus x naught, and here is the first factor is xk minus x naught. Second factor is x minus x1, and here is the second factor is xk minus x1. So just this x is replaced with xk. So x minus x1, x minus xk minus 1, and so on. So this x is replaced with xk. And this product can be written as x minus xi over xk minus xi. So I started from 0 to n. So here is you see 0, 1, k minus 1, k plus 1, and n. So I is indexed from 0 to n. So 0, 1, 2, 3, so on, n. And k, xk, uh, I is not equal to k. This should not be equal to k. Similarly here, so 0, k, 1, k, and k, k minus 1. So here you cannot take xk minus xk. Similarly, in the numerator, you cannot take xk minus xk. So that is why this is the restriction that I is not equal to k. So ln k of x simply can be written as lk of x if there is no confusion as to its degree. So if we are clear that we are actually generating the polynomial of degree 2, 3, 4, then we can skip to write ln k of x and we can simply write lk of x. For example, if you observe here, we have simply write that L1 of k because we were clear that this polynomial is of degree 1, and we can write L0 of k because we were clear that this polynomial is of degree 1. But if you want to write this, so here the first index is representing the degree of polynomial, so 1, and then the index for the coefficients. So L0 of x, L10 mean polynomial of degree 1 and the first Lagrange coefficients. L1 of 1 mean polynomial of degree 1 and the first, second Lagrange coefficients. So here is the polynomial of degree n and the kth Lagrange coefficient. So if we are clear that this is the polynomial of degree n, so we don't need to write n. We can start with lk. Moreover, lnk of xi is equal to 0 when I is not equal to k. So this is another advantage. So all the factors with I is not equal to k will be 0. And all the factors with I is equal to k will be 1. So that is the advantage of these terms. So if we have this, you see, so if 1, 1, Yeah, this we have observed here. You see the x1 minus x1. Okay, this is 0 and x naught minus x naught equal also 0, but x naught minus x1 over x naught minus x1 equal to 1. So next we can explain an example. The example 5.2.1 is determine the linear Lagrange interpolating polynomial that passes through the points 2.24 and 5.1. So we can write this unique polynomial as we have written here. So P naught of x is equal to L naught of x f of x1 plus L1 of x f of x1. So we need to compute these two terms f of x naught and f of x1, and then we are required to compute these Lagrange coefficients L naught of x and L1 of x. So if we apply this technique here, so for point x naught, y naught is equal to 4, y1 is equal to 1. So the first Lagrange coefficients can be computed as x minus x naught x1 over x naught minus x1 is equal to x minus 5 over 2 minus 5. So minus 1 by 3 x minus 5. And similarly, second Lagrange coefficient can be computed as x minus x naught over x1 minus x naught is equal to x minus 2 over 5 minus 2 equal to 1 by 3 into x minus 2. And then we can put these terms in the uh, linear Lagrange interpolating polynomial, and we will have this polynomial minus 1 by 3 x minus 5 into 4 plus 1 by 3 x minus 2 into 1, and after simplification we have this minus x plus 6. So next example is find the second Lagrange interpolating polynomial for f of x is equal to 1 over x if the first point in the domain is 2, second is 2.75, and third is 4. Okay, these we can also call these points as nodes or numbers. So use the polynomial to approximate f of 3 is equal to 1 by 3. So here in the form of summation, you can write is k equal to 0 to 2 for 3 points, because here you have 3 points. So ultimately, you will have the polynomial of degree 2. So f of x k L2, 2 is showing the degree of polynomial, and k is the kth coefficients. So P2 of x Lagrange polynomial of degree 2. It can be written as P2 of x is equal to L naught of x f of x naught plus L1 of x f of x1 plus L2 of x f of x2, where L naught of x is equal to x minus x1 x minus x2, and then these same factors can be written as the denominator, but just replacing x with x naught. So x naught minus x1 x naught minus x2, and then we are substituting the given values. So x1 x2 we have replaced these, then x naught minus x1 x naught minus x2 we have replaced these values, x minus 2.75 into x minus 4, and if we simplify these factors we will have 1.5. Similarly, for the second Lagrange interpolating coefficients L1 of x, we have this x1 minus x naught, x1 minus x naught, and the same factors as a numerator, but replacing this x with x1 or x1 with x. And after simplification, we have this term. And for the third factor L2 of x, we will have x minus x naught, x minus x1. and these factors can be replaced as a denominator, but x replaced with x2. And by substituting the points, okay, we have the term x minus 2, x minus 2.75 over 2.5. Now we replace these factors in this polynomial and we will have, so what we will have, we first, before this, we can compute this f of x naught, f of x1, f of x2. So here f of x naught is equal to 1 by 2, 0.5, f of x1. So what is x1? x1 is 2.75. So we have replaced this 2.75, okay, and we get this one 0.36363, and then f of x2 1 over 4 is equal to 0.25. Because if we divide 1 over 4, so 1 by 4 will be is equal to 0.25. And then we replace this L naught of x into f of x naught. So L naught of x, f of x naught. So what is L naught of x? L naught of x is equal to this term x minus 2.75 into x minus 4 over 1.5. So this term. And then f of x naught. So f of x naught is equal to 0.5. So in this way, just multiply this term. And then we have simplified. We have obtained this x square minus 6.75x plus 11 over 3. And similarly, this second term L1 of x f of x1, L1 of x f of x1 can be written as 0.3636 x minus 2 x minus 4, this one, and we simplified this and we will have this. Okay, and similarly the third term is this is the third factor, so L2 of x into f of x2. So L2 of x into f of x2 is equal to 0.25 into x minus 2. So this term L2 of x2 we just have written in the form of just to obtain the simplified form. So 0.25 x minus 2 into x minus 2.75 over 2.5. We have simplified this and we have got this x square minus 4.75x plus 5.5 over 10. So then we just observe again this equation 5.75. So this is actually the Lagrange's interpolating polynomial of degree 2. As we have discussed before, so now we will replace these terms which we have calculated here. So L2 of x f of x2. So this one L1 of x f of x1, this term, and the first term is L naught of x f of x naught. So this term. So we can sum up these three terms, or we can just substitute these terms in this Lagrange interpolating polynomial of degree 2. So then what we will have, the first term, this one, so x square minus 6.75x plus 11. Okay, so then the second term, then the third term. So this, we have written the term in the form, and after simplification, so we will get this x square into 0.04549 plus x into minus 0.39796 plus 1.1139466. So then after simplification, we will have this polynomial of degree 2. So now what was the question is there? So we need to approximate. Okay, question was that find the second Lagrange interpolating polynomial for f of x is equal to 1 by x. So we need to construct a polynomial that can fits the given data. So what's the given data? Given data is x naught is equal to 2, x1 is equal to 2.75, x2 is equal to 4. So we have a 3 points. So what's the degree? What will be the degree of polynomial? Degree of polynomial will be 2, because to construct a polynomial of n degree, we need n plus 1 points. So here, if we have a 3 points, we have to construct the polynomial of degree at most 2. And then what's the second part of the question is that we have to use the constructed polynomial to approximate f of 3. So here, what is the constructed polynomial? The constructed polynomial is p2 of x is equal to x square into 0.04549 plus x into minus 0.39796 plus 1.113946. So what we need to do is just we have to replace x with 3. So if we replace this x with 3, we will get the required answer. P2 of 3 is equal to 3 square into 0.04549 plus 3 into minus 0.39796 plus 1.113946, and this answer is 0.349. So if we do the simple calculation and with the calculator, what is the, if we divide this 1 by 3, we will have this, what we will have 0.333 like this one. And there is a very small difference. So it means in the in the exact calculation and the polynomial approximation, error can exist. So to improve the degree of accuracy, what we will have to do? We have to increase the degree of polynomials. So here is the difference, and the new thing is that if we have a more number of domain points, or the data set of points, or we increase the degree of polynomials, we will obtain more accurate answer. And if we decrease the degree of polynomial, we will have more errors. So to avoid from the errors or to achieve the accuracy, we must have to increase the degree of polynomial or the data points. So it's the same. If we increase the data sets, we will actually increase the degree of polynomial. And if we increase the degree of polynomial, so automatically we will increase the data points. So next example is the amount of a substance remaining in a reacting system after an interval of time t in a certain chemical experiment is given by the following table. Find value of A at time is equal to 11. So here is the table. So if time is equal to 2, we have A value of A is equal to 94.8. And if time is equal to 5, we have a value of A is equal to 87.5. And the amount of a substance remaining in a reacting system after an interval of time. So expressed time is expressed in T in a certain chemical experiment is given by the following table. Required polynomial. So what will be the degree of polynomial? We will guess from the data points. So data points are 1, 2, 3, 4. So what will be the degree of polynomial? 3. Required polynomial will be of the form as given below. K is equal to 0 to 3, f of t k, L3 of k of x. So then this polynomial can be written as L naught of t f of t naught plus L1 of t f of t1 plus L2 of t f of t2 plus L3 of t f of t3, where L naught of t is equal to t minus t1 into t minus t2 into t minus t3. Okay, so then t naught minus t1, t naught minus t2, t naught minus t3. So we have written this numerator. First we written the numerator, and you will observe there is no term in the numerator with the index 0. So what was the point t naught, t1, t2, t3? 4 points. So if we have written this 0 here, we cannot return 0 in the numerator. And once if we write these terms or factors in the numerator, we just has to replace t with t naught, and the same numerator we can write as a denominator. So